Well, on we go with our riveting review sessions for ELE 210 circuit theory. I will be going over review handout number 2. And as I said, we'll have some homework problems related to this stuff. But let's take a look at this. The whole purpose of this review is to kind of recapitulate the AC steady state analysis we did in Electronics for Technicians 2 back in the spring semester, or whenever you may have taken that class. So in problem 1, we have a series circuit involving an inductor and a resistor, and it's driven by a sinusoidal signal. Here it says 4 volts peak to peak. Probably should put the word sine in there to make sure of that for people. But since it's steady state AC analysis, we know it has to be driven by a single sine wave. So what we have, our first job here, especially being a series circuit, is we have to construct an impedance chart. Now we know that the resistance is 1 k ohms, so we know the size of that, and resistors are always at 0 degrees. They're kind of real devices. Our inductor, however, we have to compute the inductive reactance, and you may remember that formula is 2 pi FL. Our frequency is 100 kilohertz. So 2 pi times 100 kilohertz times 1.59 millihenries will result in, here we break it in 2 pi, 100 times 10 to the 3 hertz, 1.59 times 10 to the minus 3. Remember, 10 to the minus 3 is thousandths, which is milli, just like milliamps. This is henries for the inductor. So when we multiply these together, 2 pi times 1.59 gives us about 10, and 10 times 100 gives us 1,000. So we got 1,000 times 10 to the 3 minus 3, which is like 1,000 times 10 to the 0 ohms. But we decided to make it 1 times 10 to the 3, so it's 1,000 ohms or 1 k ohm. Okay, take a close look at that. There's no magic there. I just incorporated these guys cancel to 10 to the 0, but this guy is 1,000, so we can either call it 1,000 ohms or 1 k ohm. So now we have, if you look at our impedance chart, we have R1 over here. That's 1,000 ohms. XL1 here is also 1,000 ohms. So we got essentially a square, and our total impedance here, ZT, will be the diagonal of that square. So using the Pythagorean theorem, of course, this, our axes are at right angles, and this vertical and horizontal are at right angles. So we can see that ZT forms the hypotenuse between this horizontal side R1 and the vertical side XL1. So the classic Pythagorean theorem here is that the square of this side is equal to the sum of the squares of these two sides, and if I want just this guy, I take the square root of that. So I got the square root of the sum of the squares of the two sides. So XL over here will be 1,000 ohms at plus 90, and R will be 1,000 ohms at 0. And what we'll wind up with is the diagonal, which will be kind of the square root of 2 times this side, if you're into a little bit of geometry or trig. And we'll get 1.414, I probably should have said approximately, but 1.414 k ohms, and it'll be at an angle of 45 degrees. And remember that tangent to the minus 1 here, it's not 1 over tangent, it's the inverse tangent function. Some people call it arctan. So we want the angle, instead of the tangent of some angle, we want the angle whose tangent is L1, the inductor reactance of L1, divided by the resistance of R1, And that comes when they're both equal, that is a 45-degree angle. So now we have the total impedance here. We have its magnitude, 1.414 k ohms, and its angle, 45 degrees. So to get the current flowing through this series circuit, again, we're being asked to find the amplitude and phase angle of V out. Well, one of the ways to do that, is to find this total series current here. This is a series circuit. Find this current, multiply it by that resistor. And we could take this current and multiply it by that inductor and find the voltage across that inductor. We just have to keep in mind that everything now is vectors. So we have magnitudes and angles. So let's work on that resistor. But first we got to get the total current. So V total, that's 4 volts peak to peak at an angle of, sorry about that, 0 degrees, because the source is always at 0 degrees, divided by Z total, which is 1.414 k ohms at an angle of 45 degrees. So 4 times 10 to the 0 volts peak to peak at an angle of 0, the source is always at 0, divided by 1.414 times 10 to the 3 ohms at 45 degrees, we're going to get 2.828 times 10 to the 0 minus 3 amps peak to peak at 0 minus 45 degrees. Because when we divide, we subtract the angles, just like we subtract powers of 10. It's a very similar concept. So the total current is 2.828 milliamps peak to peak at an angle of minus 45 degrees. And it makes sense that the current is at a negative angle because current lags in an inductive circuit. You remember that. Now VR1, we're still using Ohm's law. We have IT, the total current, which is the only current flowing in a series circuit, and it's certainly the current flowing through R1, times R1 is equal to 2.828 milliamps peak to peak at an angle of minus 45 times 1 k ohm at an angle of 0. That's why we put our resistors on this line. The resistors are at an angle of 0 because they don't have any inherent delay. The resistors convert electrical energy to thermal energy immediately. So as we compute this thing here, we get 2.828 times 1. The 2.828 was milliamps, so this is 10 to the minus 3, and the 1 was k ohms, so that's 10 to the plus 3, and we wind up with 2.828 times 10 to the minus 3 plus 3, so that's just going to be 2.828. And I guess we should probably give it the right units of volts. At an angle of, we had minus 45, we had minus 45, and we're multiplying, say, add these together. So I guess the right way to say this is minus 45 degrees here. Boy, I'm having to do a little bit of editing, and I'm so sorry. So these guys, minus 45 plus 0 degrees, because when you multiply, you add the angles, gives me minus 45. And the voltage across the resistor lags because the current through the resistor also lags, and the resistor has no delay. So the voltage across the resistor has to have the same phase angle as the current through it. And so that's your minus 45. So we've VR1 is the same thing as V out. Okay, and that's the answer, and we're all done with that problem. We figured out how to get there. Problem number 2. Find the amplitude and phase angle of I total. Hint, use product over the sum formula for the total impedance, ZT. So here we have a sine wave voltage source driving a parallel combination of a resistor and a capacitor. So that's going to be messy. It may be, all right. 100 kilohertz, 4 volts peak to peak, same kind of deal. But all we want to do is find this total current. We want to find what's going on there. So the total impedance, we're going to use this kind of total resistance approach, continue to use it, but now it's total impedance. The total impedance here is the parallel combination of R1 and the capacitor C1 at this frequency, 100 kilohertz. And whenever you have two items in parallel, you can use the product over the sum formula. So we can use R1 times the capacitive reactance of C1 divided by R1 plus the capacitive reactance of C1. And we have to do all this taking care of the fact that these are vectors. So the sum in the bottom, we know how to do that. We know how to add together vector type things. We did it up in here, and we used an impedance chart. Well, we can pull the same trick down here. We'll use an impedance chart as if it's a series circuit, but that won't be the answer. That's just part way through the answer. We need the sum of R1 and X of C1, capacitive reactance of C1. So we note the denominator of this formula here is the same as the sum of R1 and C1. And maybe I should say this is really R1 and X C1. So we can again use the impedance to at least obtain the denominator, or the impedance chart. Once again, my bad. And so we've got an impedance chart. There's our resistor, 1 k ohm, and there's our capacitor, which will compute the capacitive reactance of somewhere. Maybe we didn't. Maybe you'll just have to trust me that it's 1 k ohm. What did we do here? 2 nanofarads I don't think is 1 k ohm. I think I've committed a bit of a faux pas here, and I just assumed the capacitive reactance. I got a feeling that this should be about 1.59 nanofarads, okay? So we'll take a look at that, and I'll put a note in the file. But let's just say this capacitor has whatever value gives us 1,000 ohms, because I went ahead and did this. We're going to have the same 1.414 k ohms is our diagonal here, our resultant vector, and it's going to be at negative 45 degrees now, because it's capacitive for one thing, and if we do this correctly, we'll come up with negative 45 degrees. So let's compute the vector product for the numerator. So this right here is the denominator of this thing, 1.414 k ohms at minus 45 degrees. So now we get the numerator. We have to multiply these together. So I got 1 k ohm at 0, that's the resistor, times 1 k ohm at minus 90 gives me 1 times 10 to the 6, because these k ohms are 10 to the 3. So when you multiply a k times a k, you're going to get 10 to the 6. The ohms units are going to be squared, and the angle will be, because we're multiplying, 0 plus a minus 90, and the result will be 1 times 10 to the 6 ohms squared at minus 90 degrees. So now we compute Z total as the ratio of the numerator over the denominator. So here we go. 1 times 10 to the 6th ohms squared at minus 90. That's the numerator we just calculated. And here's the denominator we calculated from the impedance chart. 1.414 k ohms at an angle of minus 45 degrees. Okay. Well, when you go to figure this out, we put 10 to 3 in here because this is k ohms. So you got 1 times 10 to the 6 over 1.414 times 10 to the 3. I got ohms squared over ohms. So and I've got minus 90 over minus 45. So we go do the grunt work on this, and we wind up with 0.7071 times 10 to the 6 minus 3. And the ohms, it's ohms squared over ohms, so that's ohms to the 2 minus 1, so that's just ohms to the 1. And I think anybody would have kind of done the canceling there. You cross out this one and cross out the 2 up there, and you're left with ohms. Any way you want to do it is fine with me as long as you get the right answer. So 0.7071 times 10 to the 6 minus 3 ohms at, now we're dividing so we have to subtract the angles, minus 90 minus 45 is going to be minus 90 plus 45, and we're going to wind up with a minus 45 degree result. And our angle here, 0.7071 times 10 to the 3rd ohms, is going to be, when you multiply it by 0.7071, you're going to get 707.1 ohms, because you got 10 to the 3rd, you can move this decimal point over 1, 2, 3, and then you've got 707.1 ohms at minus 45 degrees. And it's a capacitive circuit, and just because it's a parallel circuit, we still should be a capacitive type of circuit. And again, I will update with the correct value here to get 1 k ohm as the capacitive reactance. I don't think 2 nanofarads is correct, so I will update so that you get the claimed 1 k ohm of capacitive reactance. So now that we've got this, we finally got our Z total from that parallel combination. It's not something we want to just do for a living, but I just wanted to show that it can be done if necessary. Now we can find our total current by taking our total voltage, 4 volts peak to peak at an angle of 0, because our source is always at 0, and divide it by 707.1 ohms at minus 45 degrees. And so we start to do the work here, and we kind of put these things back into some notation. 4 divided by 0.7071 will give us 5.657, and volts over ohms is going to give us amps. So I'm going to get 5.657 times 10 to the 0 minus 3. We're dividing, so we subtract the exponents. Amps peak to peak at an angle of 0 minus a negative 45. Again, we're dividing, so we subtract. And the result there is that we get 5.657 milliamps peak to peak at a positive 45 degrees, because the total current of a capacitive circuit should lead, and that's what we get. We get our current leading in a capacitive circuit. And that's the end of this particular review. I will, like I said, I will get you the correct value here so you can kind of see how that all works. But for now, we're just assuming that whatever this capacitor is, it has 1,000 ohms of capacitive reactance. And of course, capacitors point straight down at minus 90 degrees. Inductors point straight up at plus 90. So there's our kind of review of our basic steady state analysis, and I hope that helped, and you'll have this handout updated with this value taken care of in there, and we'll see you next time. I think we'll do the next lecture. We'll have some review and start to move us into our first material, which is Thevenin's and Norton's theorem. It's how to simplify sources to make problems easier to calculate. All right, take it easy, and we will see you next time. Bye-bye.